Okay. So classically, we define something called master constraint, and this master constraint is just a non-degenerate quadratic form of all the earlier constraints. QAB, Q is an inverse metric, CA, CB. Okay, so it can be using, so this is using CA, CB, so using CJ to modify diffeomorphism constraint. So it's looking like this. C squared plus 1 over 4 CJ, CJ. Well, repeating index means summation. Okay. And you can see this is a non-degenerate quadratic form. So M is a non-degenerate quadratic form. This is a form of C and CJ. Okay. All right. Suppose we write well in terms of CI. So the idea is like M equals to something like Kij CI CJ. Well, this so non-degenerate and positive quadratic form. Positive quadratic form. So here this Kij is a positive semi-definite matrix, right? And you can imagine, suppose you have a set of constraints. In general, suppose you have a set of constraints CI. You can define a master constraint just by making a quadratic form, making a positive quadratic form of these CIs. And if this kernel, what we call it, the kernel of this quadratic form, this Kij, it is a positive matrix, right? So this is just an infinite dimensional generalization of, well, it's an infinite dimensional version of the master constraint. And here you got to see this is C square and CJ square. And clearly, classically, this is a just a equivalent constraint. So M equals to 0 if it's equivalent to C equals to CJ equals to 0. So classically, these constraints are completely equivalent. Yeah, and well, C and CJ equals to 0, M equals to 0, obviously. And M equals to 0 because this is just a positive quadratic form, then C and CJ must be 0. Okay. And now, okay, so which means that we can just replace the classical constraint C and CJ by a single constraint M. So this is really a single constraint because you are integrating over three-dimensional space, and M is just a single constraint. And the classical constraint algebra of M is just trivial because it is a single constraint. Constraint algebra. It is just M and M itself equals to 0. Yeah, because you only have a single constraint. You don't have infinite number of constraints anymore. So you have only a single constraint. And this is really trivial constraint algebra. Okay. Yeah, so we have only a single constraint. All right. Now, so this is the classical level. So classical level, we can define a master constraint which collect all the constraints into a single constraint. But well, when we do the quantization, yeah, we can still do quantization for the master constraint. Quantum master constraint. Okay. Well, the quantization is very much straightforward. You can write down your constraint operator because you know how to quantize C and CJ. Okay, so you write the master constraint is the sum over all the vertices. It's a quantum for discrete analog of the integration over three-dimensional space. And then you have the operator version of C. Well, here there's a little bit different because you have a square root of Q at the denominator. Well, the reason why you have square root of Q is because because the Hamiltonian constraint and diffeomorphism constraint, they are density of weight 1. So square, you will get density weight 2. But density weight 2, you have to divide a square root of Q to get a quantity of density weight 1. Yeah. And density weight 1, if you integrate over 3 space, it is a diffeomorphism invariant quantity. It is a coordinate independent quantity. Because for any integral, when we learn integration, so for this kind of integration, it is something independent of coordinate, right? Some function. So this kind of quantity, this is a coordinate independent integral, right? Otherwise, if you don't have this determinant Q, it will depend on coordinate. Okay. Remember for example, the Einstein-Hilbert action. So you have to divide a determinant Q to remove the density weight. All right. So now you have to, therefore, you have to define some operator, which is C, not exactly C, but C divided by determinant Q to the power 1 over 4. C, and you have to define this kind of operator and dagger, and determinant Q 1 over 4. This operator. So the first operator is a dagger of the second, and also plus factor 1 over 4. Q J dagger. Okay, so what is this operator C or Cj divided by 1 over Q to the power 4? It is more or less the same operator as before, but you have to just change a little bit of your volume operator. So what is this? This is equals to just see our earlier Hamiltonian constraint operator, but you have to do some replacement, replacing the quantity HHV, okay, by 2 times H inverse. You have to replace V by square root of V. Okay, and what is the square root of V? It is just the Q square, Q operator square, and take the factor 1 over 8. Okay. So why you replace the square root to square root of V? Because because if you consider the boson bracket, H boson bracket H inverse square root of V. V is equals to just 1 over square root of V. Boson bracket. Okay, and this 1 over square root of V, it is just the discretized version of this determinant Q, 1 over 4. So this is something like this is just a discretization of determinant Q of 1 over 4. Okay, because square root of determinant Q, it is corresponding to volume, but determinant Q 1 over 4 is just square root of volume. Okay. So therefore, this is just by a simple replacement, you can construct the operator corresponding to CV divided by determinant of Q to the power 1 over 4. Well, similarly, the other operator CJ guy is just a similar. It's a similar, and you just replace the same factor by the volume by square root of the volume. Okay, and now, however, the reason why I put a dagger in front, because this operator is not exactly Hermitian. So if you review our previous lecture, that the operator we define, it is not exactly Hermitian operator. So when we do the quantization, this is a quadratic form. So it has to be a symmetric quadratic form, but now in the quantum level, it has to be Hermitian quadratic form. So therefore, the operator in front, it has to be a dagger, and the operator in the back, it is not dagger. Here because both CV and CVJ are non-Hermitian. Okay, so that's why when you construct the quadratic form, you have to put a dagger in front. Okay, but now although C and CV they are not CJ, they are not Hermitian. So CV, they are not Hermitian. The master constraint operator, it is Hermitian. So when you write your master constraint to be C dagger C, and the result it is Hermitian. So the master constraint it is Hermitian and positive. Positive semi-definite. Okay, because this is of the shape C dagger and C. Okay, so from this from this expression, it is clear that it is so firstly it is a Hermitian. If you dagger formally, if you dagger this M, well, you just get the same operator. And secondly, why it is positive definite? Suppose you consider some quantity. Well, let's do a simplified version. Let's consider a matrix element. Well, the expectation value of quantity like C dagger C. Okay, this is just equals to C operating on psi and C operating on psi. Right, and then well, remove the dagger to the psi in front, and this is definitely positive, semi-definite. Okay. So that's why this operator M is a positive semi-definite operator. And then in functional analysis, that whenever you have an operator which is Hermitian and positive semi-definite, and there's a theorem saying that this operator admit a self-joint extension. Admit a self-joint extension. Okay, so this extension is usually called Friedrich extension. This is a standard result in functional analysis. Okay. All right. I'm not sure you are familiar with result that Hermitian in quantum mechanics or in functional analysis. Hermitian and self-adjoint, they mean two different levels. It means two different things. So Hermitian just means the operator dagger. Well, self-joint, it means that the dagger of this operator is the same as the operator, right? But the same means that they have the same domain of definition. But Hermitian is weaker. Hermitian, it means something weaker than that. So therefore, I'm given an operator. You first make the dagger. Naively, I'm using the standard procedure to make the dagger. Right. Okay, so the standard procedure, you how to define a dagger. Psi is given by psi c operating on phi. Let's say an operator is equals to O dagger psi phi. Okay, and this is the way to define dagger. The dagger is defined with respect to the inner product. And then whenever you find the dagger operator, you have to find the domain of definition for this dagger. And usually for general operator, although Hermitian, it means that you can replace this O dagger in this equation by O. It means Hermitian. Yeah, and however, in this equation, the Hermitian doesn't really mean that this operator is the same, because they may have different domain of definition. Yeah, and the self-joint extension means that usually you can the operator, it is self-joint. It means that when you get the dagger operator, or when you find this operator is Hermitian, you can always extend the domain of definition to find a bigger domain of definition, such that these two operators become the same, such that the O dagger and O becomes the same. Okay, so this is usually called self-joint extension. Yeah, and whenever an operator, you find a self-joint extension for this operator, and this operator is called a self-joint. And you can really say that O dagger equals to O. Maybe I write more explicitly. So well, let's put it here. Hermitian means that psi O phi equals to O psi phi. Okay, and self-joint means that O equals to O dagger. O equals to O dagger. So these two equations, they are not exactly the same. Yeah? And first equation, Hermitian, is weaker than self-joint. Well, self-joint definitely implies Hermitian, but Hermitian not necessarily implies self-joint. Yeah? So when Hermitian operator admits a self-joint extension of their domain of definition, then we can say that the Hermitian operator is self-joint. Yeah, and why we need a self-joint? The reason that only for self-joint operators we can find eigenvalues and eigenspectrum. Yeah. Only the Hermitian is not so necessary. And for Hermitian, in case you have infinite dimensional Hilbert space, well, Hermitian operator doesn't really imply that you can find spectrum. You can find eigenvalues, right? Although, of course, and in linear algebra, in finite dimensional spaces, Hermitian equivalent to self-joint, then of course you can always find eigenvalues. But for infinite dimensional Hilbert space, self-joint and Hermitian, they are not the same. Only for self-joint operators, you can find spectrum. There's a spectrum theorem for self-joint operator, but for Hermitian operator, it is not. Sometimes you don't find spectrum. You don't think to find spectrum. Okay?
Is there any example?
Sorry?
Is there any example? Which is
example?
Yeah.
Any example? Let me see. Because most of the familiar example, it is it's always self-joint. I mean, the quantity you study in quantum mechanics, it is always self-joint.
Yes.
I don't have a simple example in my mind, but what I can tell is that for spectrum, in functional analysis, the theorem is called a spectrum theorem. Spectral theorem. It tells what kind of operator can be decomposed, can be diagonalized, and what kind of operator is not. So it implies that the self-joint operator can be diagonalized, but Hermitian operator is not.
Okay.
The reason is just the problem of domain of definition. You have different domain of definition, then yeah, it's not completely clear.
Okay.
Well, but one thing I can mention is that well, in quantum mechanics, you always assume that you have a Hamiltonian, right? Of course, yeah. In quantum mechanics, you always have a Hamiltonian. Well, in quantum mechanics, your Hamiltonian is well, kinetic term plus potential, p squared divided by 2m plus a potential, right? And let me write Hamiltonian. Well, in quantum mechanics, p squared plus 2m plus volume. Sorry, not volume. Plus potential. Okay, so and you always assume that your Hamiltonian, you can find eigenvalues of your Hamiltonian. Well, otherwise you don't find energy, right? And the energy, your energy of the system is always the eigenvalue of this Hamiltonian operator, right? So which means you assume that you can find, you can always diagonalize your Hamiltonian. But why you can assume that? The reason is that, and so firstly, you construct a Hamiltonian is always Hermitian, right? And whenever you construct a Hamiltonian, you always firstly check it is really Hermitian. And secondly, it is always positive. When you construct Hamiltonian, you always also check that your Hamiltonian is a positive operator. Otherwise, your system is not stable. Suppose it's not positive definite. So, but then this two property implies that it is self-adjoint. You can always find a self-adjoint extension by this theorem. Whenever you have an operator which is Hermitian and positive semi-definite, you can always find a self-adjoint extension, which is this Friedrich extension. And then it guarantees that in quantum mechanics, your Hamiltonian is self-adjoint, and you can find energy eigenvalues. Yeah. So that's how it impact even quantum mechanics. Okay, so probably it's not exactly answering your question, but probably help you to understand this.
Okay.
Okay, so now the conclusion is that here we can always view this master constraint operator as a self-adjoint operator. Therefore, this master constraint operator can be viewed as self-adjoint operator. Self-adjoint operator. Okay. Well, being a self-adjoint operator, in principle, this master constraint can be diagonalized. Can be diagonalized in principle. In principle. Okay. Well, and secondly, well, when you look at constraint algebra, it's just trivially satisfied because you only have one single constraint. You just avoid the problem of a constraint anomaly. Well, at least at the formal level. Trivially no anomaly. Yeah. So classically, you just replace all your earlier diffeomorphism constraint, Hamiltonian constraint into a single Hamiltonian constraint because just you have a single operator. Yeah? And of course, this operator commutation relation itself equals to 0, trivially consistent with classical constraint algebra. So then trivially, you have no anomaly. Right, and then when you look at the when you impose a constraint, you impose this master constraint strongly. So quantum constraint equation. Quantum constraint equation is the master constraint operating on state equals to 0. So it's not individual Hamiltonian constraint and diffeomorphism constraint operating on state equals to 0, but this master constraint operating on state equals to 0. Right, and you can view this equation is just the eigen equation of a master constraint with 0 eigenvalue. So the solution solution is nothing but solution spans, again, solutions span physical Hilbert space. But this physical Hilbert space is just the eigenspace of master constraint. Eigenspace of hat with zero eigenvalue. With zero eigenvalue. Okay. So now at least you can define the. I mean, formally you can define this physical Hilbert space. It's well defined. Well, so this is somehow one advantage than the earlier naive procedure. That the earlier naive procedure, let's review the naive procedure. We define individually constraint equation for Hamiltonian constraint for infinite number of Hamiltonian constraint and infinite number of diffeomorphism constraint. But we have to looking for common solutions. Yeah, and so firstly, it is difficult, and secondly, it is even not well defined because all those operators are not self-adjoint operators. They are not even Hermitian. They are not self-adjoint operators. And well, how to understand this equation and how to understand the physical Hilbert space? You don't know whether those Hilbert spaces exist or not. And in addition, there are anomalies, and you have to. Those equations are not enough. You need to impose additional equations due to quantum anomaly. Okay, so you don't know whether the physical Hilbert space even exists or how to define the Hilbert space. But for master constraint, it's very clear. So the physical Hilbert space is well defined. This is the master constraint is a self-joint operator, and the physical Hilbert space is nothing but the eigenspace of master constraint with zero eigenvalue. Yeah? And it's like looking for ground state of the Hamiltonian. If you make analog, if you view this master constraint is analog to a Hamiltonian operator in quantum mechanics, and then this is nothing but like looking for ground state of the Hamiltonian. Yeah, and this is a advantage of this master constraint. At least conceptually, it makes a lot of things well defined. And secondly, why we say this is a weaker version of the constraint equation is because this master constraint equation is weaker. Let's say it's weaker. Let me say quotation mark the weaker. This is not completely rigorous. The argument is completely rigorous, but some in some sense it is weaker than the earlier constraint outputs. So this is CJ equals to 0. Okay. Because let's just put a naive version of master constraint. Let's say master constraint is something like we see. Forget about this square root, determine Q, square root of volume and so on. Let's say C. Okay. So let's consider this kind of master constraint. Okay, and then Ci optimum psi equals to 0 implies Ci equals to 0. Well, it implies master constraint optimum psi equals to 0, but not the inverse. But not the inverse. Okay, but not the inverse at the quantum level. Okay, because forwardly you can, whenever you have a constraint equation, you can imply the master constraint equation. But suppose you have a master constraint equation, you can imply the individual constraint equation. Yeah, that's why the constraint, the earlier constraint equation is stronger than the master constraint equation. So that's exactly what we need, right? And the earlier constraint equation is too strong, and so that the physical Hilbert space is too small. Okay? And then we want to have a weaker version of the constraint equation. So this master constraint may be viewed as a resolution of quantum constraint anomaly. So maybe a resolution of quantum constraint anomaly. Okay. Well, I say it's maybe, but because this is not still there are still a lot of debate on this. There are still a lot of people don't like master constraints because it looks still too naive, because you just make a quadratic form of the earlier constraints, and then you're looking for the constraint algebra is trivial, becomes trivial. Yeah, then of course you don't have a number. But seems you need to look at the physics behind this procedure in order to decide whether this is there's no problem or there's still some problem going on there. But still, the constraint equation and this master constraint equation, it is still very difficult to solve, because although conceptually you can define the physical Hilbert space as eigenspace, but to practically compute states in this eigenspace, it is still very hard, because again, the problem one is still there, and the operator is still non-polynomial. The master constraint is even more complicated than the earlier constraint operator. So yeah, and to actually solve this constraint, it is still very hard. Okay, and that's why to extract the physics and to decide whether this is a resolution of the constraint anomaly is not 100% clear. Although it looks like a good procedure, but it is not 100% clear whether it is the finally correct procedure for quantum gravity. Okay, so this is the situation of the constraint and constraint anomaly and master constraint, and those procedure. Let's say these are the result before 2008, 2007. Yeah, and now we are wondering if there's any better procedure than this. How to solve? We see when we do the quantization of the constraints, we left with two problems. One problem is you see it is very hard to compute. Secondly, you have anomalies, quantum anomaly, and also discretization anomalies in your formalism, and somehow master constraint can help a little bit, but it's not 100% helpful, especially in problem one, in a computational perspective. Now our question is how to solve both problems, how to resolve both problems. One and two. So now you are really in the frontier of this loop quantum gravity area. So you are facing directly to the problem of the formalism. So exactly this whole problem is actually existing in this field for a really long time, for at least 10 years. People realize these problems, and people try to solve this problem, but in the last 10 or 15 years, people didn't really succeed to solve these two problems, at least in the formalism of constraints. But there is another procedure which hopefully solving both problems. And this procedure, this is called reduced phase-space quantization. Reduce the phase-space. space-based quantization. And the idea for this reduced space-based quantization is that you are going to solve those constraints classically. Solve constraints. Solve constraint classically and then quantize. Okay, so as you can see, and all those problems are coming from that you have some complicated constraint in general relativity. Okay, and suppose you resolve those constraints at the classical level, and then do the quantization, and then seems that you don't really need to deal with those constraints anymore, and then you don't have all those problems, right? And then that's why this reduced space-based quantization formalism is very much promising. Okay, and it is probably the best procedure for loop quantum gravity nowadays. Okay, and this reduced space-based quantization is invented by Christina Wiesel and Thomas Tiemann in 2007. And probably this is maybe for at least for canonical approach of loop quantum gravity, and all the approach we follow in this lecture, what we call canonical formulation of loop quantum gravity. And this reduced space-based quantization probably is the most useful procedure, at least for nowadays, for recent development. Useful reason. Okay. And by the way, so what I say, solving those constraints classically and then quantize, and seems that you are not really quantizing constraints. You may wonder, well, I mean, what you learn, you spend a lot of time in the last few lectures to learn how to quantize Hamiltonian constraint, invariant constraint, and in the end, you find it problematic, and seems that you are wasting your time. But the answer is that no, you are not wasting your time. So in the end, although you're solving those constraints classically, and then you will end up with some other operators, which we call physical Hamiltonian. Yeah, and when you solve the constraint classically, and then still you need to define your time evolution, right? And in the end, you will end up with something called physical Hamiltonian. And this physical Hamiltonian is just some certain combination of the earlier Hamiltonian constraint and diffeomorphism constraint. Yeah? And when you're quantizing the physical Hamiltonian, you are actually using the earlier operators for Hamiltonian constraint and diffeomorphism constraint. So definitely, the earlier work on quantizing Hamiltonian constraint, diffeomorphism constraint is definitely useful, even in the reduced space-based quantization procedure. Okay, so but I think that now is a good time to stop, and so I think for the next lecture I'm going to give you an overview about reduced space-based quantization. I'm not going to be discuss very much 100% detail about this reduced space-based quantization, but I'm just giving you a idea and also use some useful result, which is helpful for